Okay, so talk is about some consequences of a problem of assumed hardness of a problem about expansion of small sets in a graph. So let me sort of sketch what the problem is, how it connects to some other known problem, and then we can see what the consequences are. So I mean, one problem which everybody knows here probably is the unique games problem, which is some constraint satisfaction problem. For this purpose of this talk, okay, maybe I can define it right now. So in this problem, you are given a graph, and you have to label the vertices from some label set R, and on every edge you have a permutation written, some different permutation for every edge, from labels to labels. And the goal is that the labeling should be such that when I permute the label of u, so the permutation is uv. When I permute the label of v, I get the label u, I get the label of v, and you can assume pi uv and pi vu are inverses. Okay, so this is the problem. It's conjectured it's hard to decide if you can satisfy 99% of the constraints or just 1% of them, and it has a lot of consequences. Once you assume the hardness of this problem, it gives optimal hardness results for a lot of other problems. What is the small set expansion problem? Well, again, so before I get to that, let me just define expansion for all of us. So if we have a graph G and we want to define the expansion of a set S in that graph, we just say what is the number of edges that go from this set to its complement divided by the volume of the set, or how many edges are incident on vertices of S. And for the purposes of this talk, let us talk of regular graphs only, which means that it's probably also okay to write d times the size of S, where the d is the degree of the graph. And another way to write it, which is somewhat nice, is let's think of this as maybe up to a loss of factor of 2. Probability that I pick a random edge, one endpoint lands in S and the other lands outside S, and this edge I am picking is maybe directed, divided by the probability that I pick a random edge and the first endpoint lands in S. This is the same ratio, maybe up to a factor of 2. And so this is just the conditional probability that the second endpoint is not in S, given that the first endpoint is in S. So this is what I mean by expansion. Okay, now the problem small set expansion with some parameters, say eta delta, is the problem of distinguishing between the following two cases. Case 1 says that there exists a set which is small and for which expansion is very small. So what this means is that there exists a set S such that the volume of S, or say this probability we call the measure of S. So the measure of S is small, delta, and the expansion of S is less than or equal to eta. And case 2 is for all S which have this measure, so this one says the expansion is extremely small, this one says it's very large for all sets, and the question is to distinguish between these two given a graph. And it was conjectured by Raghavendra and Steuerer in basically last year that the paper will appear this year. That for all eta there exists delta such that so the conjecture would be, okay, you would like to say NP hard, that would imply NP hardness of unique games. But basically if you assume some kind of hardness for this problem, you get similar hardness for unique games, maybe if you assume some. Okay, so this is the problem, and what kind of consequences or what connections do we know with this problem? Saying is that
you're going to have the flexibility in eta can make up for flexibility in delta or something.
Right. So what I'll say is that this is the problem I just defined, where you want to have expansion either less than eta or more than 1 minus eta sets of size delta. This sort of is equivalent to a problem, and if I change eta by a factor of m, then I can say that this is equivalent to hardness of the problem with which is this, in which the yes case is the same, or the first case is the same, that there exists S and expansion. But in the second case, I can change the measure by a factor of m on either side. So in this case I get a stronger promise. Not only is the expansion large for sets of size delta, but between delta over 10 and 10 delta. And if we know that for every delta, for every eta there exists delta such that this problem is hard, then you can say that for every eta and m there exists delta such that this problem is hard. And in fact it will be more convenient to work with this, but it's nicer to define this problem because it's a simpler one. Okay. The reduction between these two is not very different, these sample sets. Okay. So let me just say the connection. I mean, so what we know is that if the small set expansion problem is hard, is NP hard, say, then it implies that the unique games problem is hard. And this was shown by Prasad Raghavendra and David Steuerer in last year. And then this implies the hardness of lots of problems. Max cut, all kinds of constraint satisfaction problems, and many others. One area which one kind of problems which it did not imply or were difficult to get with this were expansion problems. Like the problem of dividing a graph into two roughly equal pieces with minimum number of edges going between them, which is balanced separator, or stronger version is minimum bisection where the pieces are exactly equal, or I mean some other problems related to expansion which I will mention. And this happened because of some kind of technical issue in all the reductions known from this problem. They had one feature which required that if you want to get a conclusion about the expansion of the resulting instance you obtain after reduction, then you kind of require that conclusion, sort of need an assumption about the expansion of the graph in this problem. And this assumption seemed to be an extra assumption on top. So if you assume that unique games is hard even when the underlying graph is expanding, and you have to be careful here, because if the underlying graph is a very good expander, this problem is not hard, it's easy, and that was shown in a paper by Sanjeev Arora, Alexandra, Subhash Khote, David Steuerer, Nishit Vishnoi, and myself. So when it's and it was conjectured, so sort of in that paper we wrote up that if it's hard on mildly expanding graphs, then you can get hardness of these problems. So that's an extra assumption that we.
Did Kotel Vishnoi show something like that if they use some kind of UGC-based hardness for sparse scat or things like that?
So in the original manuscript, they were assuming very high expansion, which was constant expansion. That was falsified by this paper. But then in the conference version, we wrote up sort of slightly different assumption, which was dividing the graph into 3 pieces with some expansion properties. Even that is false, and sort of in the journal version which we have is there is a assumption with mild expansion on the original graph, which shows hardness.
So that comes actually from this paper?
So that's in the journal version of this paper, which is not published, but I mean it's not a very difficult reduction, it's something you would guess. Proof.
Paper that has inequality gap also had some unique games hardness.
The proof there immediately would not go for mild expansion, but it's not too hard.
Mild expansion is not having a small number of large eigenvalues, right? For that there is an algorithm.
So here mild expansion just means, so I will come to that also, but here mild expansion just means that all balance cuts of, if I look at cuts which are say 1/4 on one side at least, have something like between something like square root epsilon fraction of edges crossing. Epsilon is when you want to, right. So for unique games you want to decide if 1 minus epsilon edges are satisfiable or only some very small number. Let's say that's also epsilon. So if you make a fairly large constant in front of the square root epsilon, that's known to be false. If you put a small constant, or actually you can, instead of square root epsilon, you can take it to be epsilon to the t for any t which is between half and 1.
Epsilon to 0.6.
Yeah, if it's epsilon to the 0.6 for example, that will give you super constant hardness. That doesn't say anything about the eigenvalue, because between eigenvalue and expansion there is a quadratic factor, which means that this is possible even when the second eigenvalue is something like 1 minus epsilon to the 1.2. It doesn't immediately, but the sort of more of those large eigenvalues mean small set expansion, and but again the kind of expansion you get degrades. I think Boaz knows that better, but
Right now, all our results, I guess, we don't know to say that graphs that have this property have a small number of
large eigen.
But your algorithm doesn't work for this case? It doesn't work better for this case?
you have to analyze how many eigenvalues, how many large eigenvalues they are, and I don't know if we can. I don't think we can show that there are that if it's an expander, a mild expander in this sense, then there are a few of them. Although I never actually thought about this this kind of definition of expansion, but I guess even if it works, I mean, at least right now, what we know how to show is at best a sub-exponential algorithm that runs it times 2 to the n to the epsilon.
Well, the sub-exponential algorithm, so the point is how many small eigenvalues you can guarantee. If you can say there are only 10 large eigenvalues, then it's not sub-exponential.
Yes, then will be much better. Yes.
The sub-exponential algorithm is always true regardless of what the expansion profile is. So yeah, when I am saying all these problems hard, at best the hardness you can get is something like 2 to the n to the epsilon, which just means that well, which one thing it means is if you want to have a reduction which proves the hardness, the reduction will have to have a blow up. Okay. What we show in this paper is that sort of this small set expansion conjecture also implies the hardness of expansion problems, and in fact also of this problem. And what is interesting is sort of how you get around the problem of that you face when reducing from unique games to an expansion problem, which is that you have to assume something about this graph itself. So it looks like we are reducing from an expansion problem, and that's why this goes away, but there is something else which is slightly different in the reduction, which I'll show you.
Is it possible to do a reduction from the other way from UG to small set expansion?
I should have said that. So this was already shown by Raghavendra and Steuerer when it's hard on expanding graphs.
But not the same definition of mild expansion or the same.
No, I was asking about the unique games conjecture.
So what they use is small set expansion instead of mild expansion.
Do we understand the difference between small set expansion and mild expansion?
No, I haven't really shown you that, but
I was asking about the unique games without expansion.
from here to small set, we don't know how to do that. I mean, that again runs into similar problem, right? You want to kind of
Small set expansion is much easier than unique games.
we don't know.
But do you have a sense whether mild expanding in this sense and small set expanding is different or unique? Can you at least show that these are all equivalent? Small set expansion, unique games when the underlying graph is a small set expander, and unique games when the underlying graph is a mild expander?
No, we don't know how to show that actually. So for this reduction, we need to assume something which is different from mild expansion, which is the small set expansion notion. And I don't know how to show the small set expansion and mild expansion of this balanced sets. I mean, I don't know how to go from mild expansion to small set expansion. In fact, that's something that will come up later. But okay, so just write the formal statement of our result and say a couple of consequences, and then we'll get to the proof. To get the results, and the most general statement, you are allowed to choose parameters q, which is a natural number, epsilon, delta, gamma, and say that whereby SSE hard just means that there is a reduction from small set expansion to this problem which I am going to write. So it's again a distinction problem, distinguishing between two cases. Given a graph H, in one case can find disjoint pieces, q disjoint pieces, which are all these graphs will be regular, which are comprising of vertices of this, such that the pieces are roughly equal and cover the graph, which means that about 1 over q, and the expansion is small. So, the graph is almost covered by non-expanding pieces. In I can partition it into equal parts. It's regular, so it's not that bad. Right. So, I just want to write it this way because it's not always clear how these parameters compare, and I'll need slightly different trade-offs for different applications. So, it's I'm just writing the result and I'll choose parameters. In most of them, it will be easy to just throw away and have equal pieces. Yes. In the no case, you say that all sort of sets or all cuts in this graph are expanding. Thanks. You want to say that this graph has a fairly good expansion, and in fact the expansion is about as good as if you would take Gaussian and perturb it a little bit. So, you take Gaussian measure on the space and perturb it a little bit, and you see if I take a region of the space, how many edges go out, where the edges are a point to its perturbed image. So, let me just and the expansion will be roughly the expansion of that graph. So, what I mean is for a set which is not too small, so delta can be made no too small. So, the number of or sort of the fraction of edges that go from S to S, which is how it is stated for a Gaussian. So, I will just state it and I will spend some time decoding this result. Okay, let me just define the symbols here. So, this is just the probability that I pick x and y, x is in S and y is in S. So, the fraction of edges going from S to S. This no, that is also normalized by the measure. So, no, so H S comma S is just the probability that x is in S and y is in S.
So it's 1 minus this times the measure of S.
Right. The expansion is the total fraction of edges incident on it minus the number of edges that stay inside divided by the volume, right. So, it is 1 minus this quantity divided by mu, and what is this symbol? Let us just call it mu is equal to the probability that I pick two Gaussians x and y, which are 1 minus epsilon correlated, which means that x is equal to 1 minus epsilon times y plus square root of 2 epsilon minus epsilon square z, where y and z are independent Gaussians. The phi inverse is the cumulative density function of the Gaussian. So, it is just the point on the curve such that this area is mu. what would you prefer? Capital? No, not G. I don't know. Script G. Doesn't matter. I mean, this is the only time it will come up, so it doesn't really matter so much. Right. So, I mean, this is like the expansion. Another model for this Gaussian is you take a hypercube and perturb every bit with probability epsilon over 2 to a random bit, and then you ask what is the expansion of a set of measure mu in that graph. If you disallow certain cuts which are coordinate cuts, then the expansion looks like this, or the fraction of edges that go out. What we are saying is, in this graph, the expansion profile is always like this for all sets of measure above delta. To get a sense of what this quantity is, when mu is about half, this is square root epsilon, or 1 minus square root epsilon, which is so the expansion is square root epsilon for that when mu is half. When so let's just calculate this quantity. Let's just apply this theorem in two cases, and we'll see what this quantity means in those cases. This is going to be bad. Okay, so let me. Is it okay if I erase this?
The no instance basically saying that above some threshold size things behave like a noisy hypercube?
Or a noisy Gaussian. Noisy hypercube, you have to qualify that when the cuts are not dictator cuts, right? It's a very good expansion for small sets, and it's mildly good. So it's something which smoothly goes toward that mild expansion of square root epsilon at balanced sets. It's very good for small sets. So I'll in two applications I'll calculate this for small sets and for sets of size half. So we'll see. So let's start with putting q equals to this theorem, and take gamma, and we can take gamma to be very small. So maybe gamma equals epsilon square. So what does this mean? This means that there exist two pieces in the graph which cover roughly all of it, S1 and S2. So as Zev was suggesting, for this case what we can do is we can just include this arbitrarily, so that we divide the graph into two equal pieces, exactly equal pieces. This is just epsilon square fraction, so it will not affect any estimates much. In the yes case, there are just epsilon fraction of edges that go between them, and again this does not affect anything much. So you get a bisection of the graph with just epsilon fraction of edges crossing. In the no case, we get say S1, which is one of the pieces. What is the fraction of edges that go out is 1 minus this quantity divided by of half, which is the measure of the set, divided by the measure of the set. Sorry, this is at least.
It comes out to be, the whole thing comes out to be something like smooth epsilon.
Yeah, so this is basically the noise stability of a cut of measure half in the Gaussian, which is this is something like 1 minus 2 over pi times square root of epsilon over 2, this entire ratio. This is the value of max cut in the graph when you look at the Gaussian. So this quantity comes out to be something like in this case the fraction of edges crossing is about square root epsilon. So, this gives you super constant hardness for minimum bisection, say, in the graph. Like in one case there is a bisection with the epsilon fraction of edges, in the other case it requires at least square root epsilon.
It's like the Shiger's inequality is optimal in some sense, like is the best algorithm.
Right. So, yeah, I mean, so you can also do, yeah, always when you get epsilon, square root epsilon is the best you can hope for by Shiger, and it achieves that up to maybe the constant. And in fact, this epsilon and epsilon over 2 is kind of there for a reason, which comes essentially because of correlated sampling, or the effect that when you have two distributions with 1 minus epsilon closeness or epsilon statistical distance, you want to draw a sample from both of them, then the with probability 1 minus 2 epsilon you get the same sample, and that ratio of 2 is actually what causes this epsilon over 2 here and this epsilon here, and we will see that in the proof. Okay, but is this application okay?
If this is hard,
then minimum bisection is hard.
eigenvalues will give you the best information. In polynomial time, this is the only thing you can do. To approximate this. Super constant is this epsilon, right?
Super constant is, yeah, you can arbitrary epsilon.
Yeah, but that affects if you want epsilon to be, 1 over log n, then but just you can assume the hardness. But
Right. So
you say you don't lose anything in this part of the, the assumption may get stronger for smaller epsilon.
this
I wonder if you, so first of all, this problem also has an algorithm of 2 to the n to the epsilon.
yes,
Yes, okay, so if you put epsilon to be
1 over log n you can.
You actually should get a polynomial time algorithm.
For that one, yes. I mean, it will essentially be some of the things in the reduction will become trivial once you do that. Okay.
What are the applications? Why do you need Q to be larger than 2 for what application?
So, for example, when you want to do minimum linear arrangement, which I just want to show you next, or when I want to get a unique game, Q will be the alphabet size of the unique game. So, another problem, which is this linear arrangement problem, is you want to put the vertices of the graph on a line. So, you want to have a ordering, I don't know, L, capital L, from n, such that the expected length of an edge is small. And so, this is the linear arrangement problem. Minimize over all L of this type, which is just arrangement of vertices on a line. Sorry? Yes. So, it is 1 to 1. It is an ordering, and this is just the length of this edge x comma y under this ordering, and you want to minimize the average length.
The length, the number of vertices between them, or is it like a?
The number of
They get integer position, so it's just distance between these two integers. Oh.
the number of vertices between them in this ordering, right? It is just this difference.
embed the graph on the numbers 1 to n, and you get length of edges, and you just sum them up.
The number of vertices is n?
Yes.
I guess +1 or -1 doesn't matter so much, but I mean, if the graph itself was aligned, then this expectation will be 1, I guess.
If the yeah, it will be 1 because
the graph was a line.
If
Yeah.
the graph itself was aligned, then it will be 1. And generally it could be worse.
yeah. So we usually look at how this compares to n. So the two hardness cases will be n times. So it will be at least n when the graph is a line. It will be it will be 1. What we see is that so suppose we have the problem or sort of the guarantee we had on small or dividing the graph into pieces, which we had on for the previous problem. Now for that graph we can arrange the pieces on the line, these are q pieces, one after the other, and just put the rest here. There is some small part. Now for 1 minus epsilon, for only epsilon fraction of the edges go between the pieces, the rest stay within. So the average length of an edge is, for 1 minus epsilon fraction of the edges, they only cross over n divided by q vertices, and the remaining epsilon fraction of edges could maybe cross n vertices, so the length could be n. So in the yes case, there is an arrangement which has this length. What I want to claim is, in the no case, all arrangements have length at least square root epsilon times n, and then I will choose q to be 1 over epsilon. So the length in the yes case will be much smaller. Why is the length larger in the no case? That so let us just embed the graph on the line, and according to the optimal ordering, and take a random cut here between n over 3 and 2n over 3. So this is an observation by Devanur, Khote, Saket and Vishnoi. Then if you take a random cut here, then the fraction of edges crossing this cut is at most the fraction of edges crossing this cut is at most this number, which is just what is the length of an edge and what is the point on which I cut. If all the edges were crossing this and within length n over 3 and I was susceptible to cut them, this would be the fraction of edges crossing this cut, which is in expectation. And but I know that the fraction of edges crossing this cut is at least square root epsilon in my graph, because all balanced cuts have at least a square root epsilon fraction of edges crossing them. So that means that the minimum ordering will have cost at least square root epsilon times n. And so here you get something which is order so yes case will be epsilon n if I choose q to be 1 over epsilon. Okay, so does the statement of the theorem make somewhat more sense now, or do you want me to work out something else for this?
So far you really just use it for balanced cuts.
So far I have used it only for balance cuts. Okay, so if I use it for
But anyway, yeah, it's okay.
well, so let me just say what the unique games solution is, or how you get hardness of unique games, and there we'll use it for sort of unbalanced cuts, and there is one more thing. But
You didn't plan to do it.
and I just want to mention it a little bit. So the unique game, so the graph actually has more structure. So this doesn't follow from the theorem statement, but from the proof. The graph H we get is actually more structured. It's like the label extended graph of a unique game, the graph H. So it looks like the following. I mean some matchings. It's a lift of a graph, and some others. And these sets S1 to SL, which are the partition of the graph.
This is the graph you get from the reduction from SSE.
Yeah, so the graph H has this structure, which is the graph again. The sets S1 to S sub L look like this, that in this graph you can do it. So each of these clouds has q elements, and each Si picks exactly one from each cloud. So if you think of this as a unique game by sort of this being the constraint, this being a vertex of the unique game, the entire cloud, and these the label set being size q, then these sets S1 to Sq are just assignments to the unique game, which is just one copy of the original of this underlying constraint graph. And this means that there are epsilon fraction of edges which are unsatisfied, which sort of go from this copy to another copy of the graph. So the yes case actually means that 1 minus epsilon fraction of the edges in this underlying unique game can be satisfied. Now in the no case, if you consider any arbitrary assignment to this unique game, if I pick the corresponding vertices in each cloud, that's a set of measure 1 over q. And what this tells me is the number of edges that stay inside, or the fraction of edges that stay inside, is this quantity, which is something like 1 over q to the 1 plus epsilon over 2 for large q. This is the, and you normalize it by the size of the set to actually get the fraction of edges in the unique game that are unsatisfied, or that are satisfied, which stay inside. And so you get that in the unique game, just 1 over q to the epsilon over 2 fraction of edges are satisfied. And also, so in the no case, the unique game is unsatisfiable, and moreover that if you take any set of any measure mu in the unique game, it has expansion according like the Gaussian. So this same conclusion gives you unsatisfiability as well as expansion, because it's a conclusion about expansion of the label extended graph. Is that okay?
The epsilon over 2 is what you get. What is sorry, so we get 1 minus epsilon in the yes case.
Yes.
And 1 over q. What is the
It's exactly this number. Yeah, I mean it's 2 minus epsilon to be precise, but so the optimal hardness for the unique game would be something like this, that it's hard to distinguish between 1 minus epsilon satisfiable and 1 over q to the epsilon over 2 satisfiable. Q is the alphabet.
So why it looks like your sets are of size exactly 1 over q? Why the gamma thing?
Maybe it is unnecessary. I mean, okay. some point I thought for some application it was good to have the gamma there, but maybe I was just wrong. Yeah, you can always probably forget this. Okay, should we take a 5-minute break and then get to the proof? Let me recap the reductions from say small set expansion problem to unique games. The attempted reduction from unique games to sparsest cut, which fails because of the underlying assumption, and see if we can combine. If we combine the two, we can get around it. So I'll present.
You are going to start from this problem and go to sparsest cut, right?
No, from this partition problem to sparsest cut is easy, right? That was just you take q equals 2 or
Yeah,
right.
No, that was bisection. Yeah, okay.
But
Yes.
the yes case that you get a bisection, the no case any 1/3 2/3 balance cut has Gaussian expansion of 1/3 2/3. So sparsest cut is easy easy to get the hardness for. Also. Sparsest cut is hard if you know the partition problem is hard. Now I want to prove the partition problem is hard starting from small set expansion. Instead what I will prove is the partition problem for size 2 maybe, or let me just try to prove that sparsest cut is hard starting from small set expansion or starting from even unique games, let us say. See where that has a problem, the reduction from unique games to sparsest cut, why that does not work as such, and why if the unique game is actually coming from a small set expansion problem, how can we get around that problem. And so there is some way to combine these two reductions and slight modification which works. I will mention a simplified version and the full version later. So let me start. So first of all, you are given a graph with this small set expansion problem. So in one case there is a small set of measure delta in the graph which has expansion less than eta. In the other case, all sets of measure delta or some region around delta have expansion more than 1 minus eta. And you want to conclude, you want to get a unique game, a constraint satisfaction problem out of this. So this reduction is by Raghavendra and Steuerer, and the reduction is the following. You pick again a slightly more simplified version of the reduction. You pick r edges from the graph with r to be around 1 over delta, and then with the hope that only one of them is from both points are from the set, from the so with the hope that you are looking at this exactly one, yeah. And then you randomly permute each set of endpoints and give it to two provers, or think of them as two different vertices of the graph after random permutations. So let's call this set U, let's call this set V. And the constraint, so let me describe it as a two prover game. Every time I say two provers, you can think of this as two vertices of the graph, and what they say is the label for those two vertices. So you give this set to one prover, this set to another prover after permutation, and their job is to pick one index between 1 and r each for the permuted set, such that when I revert the permutations on both, they have picked the same index, or they have picked two endpoints of each edge. If the graph has a set of size 1 over r or equal to delta, which is non-expanding, then if I just look at what one prover gets, he gets r random vertices in the graph, and with probability about 1 over e, exactly one of them lands in this non-expanding set, because it is a binomial with expectation 1, and what is the chance it is equal to 1. And conditioned on the fact that this prover gets exactly one set, this prover gets exactly one set with at least probability 1 minus epsilon after conditioning, one vertex in this set. And so both of them just they look at their tuple which is after permutation, they look at that, and if there is a unique vertex from this non expanding set, they answer the index of that vertex, otherwise they just answer randomly. And with probability about 1 over e, both of them manage to pick the same vertex. Let us leave this with the caveat that it only works with probability 1 over e. It's yeah, I mean it's a unique game, but because the constraint is just that they have to pick the same index after reverting the permutations. So the constraints are permutation constraints. They succeed with probability only 1 over e times 1 minus epsilon, close to 1 over e, not 1 minus epsilon. The constraints are unique. The answering is the strategy is not that good. So let us just say that that is the reduction for the time being. Then let us do the reduction from unique games to sparsest cut, which is a sort of a standard style. Okay. So in the no case, what they are doing is somehow, given a subset of vertices, they are with maybe probability 1%, they are somehow always figuring out an edge, or both of them are managing to pick up indices which are endpoints of the same of an edge. And so what you can show is that if they succeed with some probability zeta, then you can find a set of measure about zeta over r, or zeta times this delta, with expansion one minus zeta over 4 maybe, but something close, something like that. So if they are managing to pick up this set, what you say is that look at how does a single vertex influence their outcome. So you say, if I just look at r minus 1 vertices, and then if I add this a particular rth vertex, what is the chance that that vertex is picked by the provers? So for every set u of r minus 1 vertices, what is the chance that when I add some special vertex, the answer is actually the index of that special vertex? For the vertices for which this chance is very high, you define the small set or a non expanding set to be comprising of those vertices. So it is trying to mimic the argument we did in the completeness. The analysis is a little more tricky, and there is some noise you need to add to the reduction for that to go through.
So we ignore the noise and it won't matter.
Yes, we will ignore the noise for this part.
The noise on the side.
No, so what they do is with probability 1 minus I will call this epsilon sub v, they keep this edge. With probability epsilon sub v, they replace both endpoints by random vertices, completely random vertices. So the sizes are the same.
They take another epsilon r random. They send also, in addition to this, they also send an
epsilon
random vertices to both pools.
Right, but this noise parameter will be smaller than some other noise parameters that will be coming in, and this won't matter for most of the arguments we will do.
Similar to the reduction, the
In
low bound on matching.
Okay.
Where we need to add another vertex for a similar type of reason. But
the other, the reduction from now a unique game to sparsest cut is the following. You are given a unique game with some constraint and some alphabet size r. What you do is you replace each vertex by a hypercube, then you generate
So R is changing to 2 to the R.
yeah, so you replace each single vertex
No, I
by
understand, but the R that is upstairs that was a unique game will turn into 2 to the R when you use it for the reduction to sparse itself.
no, this R will be the alphabet size of this unique game, and then a single vertex will be replaced by 2 to the R.
So the hypercube has 2 to the R vertices?
The hypercube has 2 to the R vertices, it's hypercube of dimension R. And again, let me describe the as a 2 prover game to check sparsest cut, which is what they do now is suppose this constraint is between u and v, and then we have the constraint sort of that if we have an assignment for u, if I permute it by the label pi uv, then I should have the assignment for v, that is the constraint. And so what the provers now what we do is now put an edge between 2 vertices here in these hypercubes, and the edge is obtained as follows. You pick x sub u here, x sub v here, or actually let me just call these vertices a and b, it will be easier to work with what I get later. So I get I pick 2 strings x sub a and x sub b, which are binary strings of length r, and are 1 minus epsilon correlated, which means the corresponding bits are the same with probability 1 minus epsilon and are rechosen independently with probability epsilon. And then I put an edge between so I look at x sub b, say the permutation is such that it shifts everything by 1 bit forward. So, it moves the second bit to the third bit, the third bit to the fourth bit. So, I do that on x b. So, I maybe cyclic shift, take a cyclic shift which is 1 forward. Now, if there is a good assignment, which means that there is a labeling which satisfies it.
You just connect them with the noise graph.
Yeah, after permutations.
Yeah, well, the permutation might as well think is identity.
Okay, fine. So, if the permutation is identity, then I just connect them with the noise graph.
Between the different hypercubes
Yes.
that have an identity.
So, some noisy graph. Okay. Now, you want to say that if the unique game is highly satisfiable, then there is a good strategy. That strategy is easy. Then if the label for this is 2, then you answer according to the second bit of the binary string that you get. So, that will give you 1 minus epsilon, because the chance that across this edge, if the permutation is identity, both of them will answer according to the second bit, and the second bit was flipped across an edge with probability only epsilon. Exactly. So, that is the standard way to answer for unique games completeness. In the soundness, you would like to say that if this game has if the unique game is highly unsatisfiable, then you can't implement this kind of a strategy. Then you would like to say lots of edges cross these cuts, but that is unclear, because maybe there is a cut in the original graph. So, remember, all these noisy edges were placed along the edges in the original graph. You looked at an edge, looked at 2 hypercubes and placed an edge there, but maybe the original graph looked like this, which was just 2 disjoint pieces. Then I can look at a cut in the original graph and look at the corresponding cut here, which means that I label all of them on the left side, all of them on the left side if they are on the top part, and the right if they are on the bottom. And that is a cut in this graph obtained after reduction, which cuts essentially no edges, or in this case no edges at all. Right. So, the problem is that it is a gadget based reduction. I replace every vertex of the graph by a gadget, and so cuts in the original graph are also valid cuts here. And That's why I need something about the expansion of the original graph to make any conclusion about cuts here. Okay, is that point okay? So let's see how we can modify this reduction if we actually try to see what's happening when we combine these two. Okay, so in the first part we are picking a matching which corresponds to an edge in the unique games graph. So an edge in the unique games constraint graph is basically G to the R. Yeah. It's a weighted graph.
So you don't want to argue later about using this randomness. So you describe this construction using randomness.
Yeah, but they are all are tuples also. All are tuples of edges.
You mean the randomness used in generating these strings?
So there is no randomness.
No, you think of them as weights. So you put an edge between every pair XA and every XB with the weight is equal to the probability that is generated. Okay, so an edge here corresponds to a matching in the original graph. Now what you do there is you pick a binary string. Let's say we pick one binary string and then take two perturbed copies. So what does a binary string mean? We sort of put binary, choose a subset of these edges. Maybe some of them are ones and some of them are zeros. And then we tell this 0 or 1. Right? So this is the strings were 0, 1 to the R, which means there is one bit for every edge. And then we give these bits to the two provers, maybe sometimes perturbed a little. So sometimes we flip the bit, but most of the times we don't. So on and so forth. Yeah, I mean it's equivalent the experiment if I just. So what is going on? I picked a subset of the edges, and then I told this prover the corresponding subset of vertices that I chose, and I told this prover the corresponding subset of vertices with some noise. Now here's an idea. Instead of telling them a bit string, which is look at the vertices V1 to Vr and the bit string 0, 1, we just tell them vertices corresponding to the ones, which is a subset of these that we actually chose. If I think of them as subsets, I can say that I actually give the subset and don't give the subsets corresponding to zeros. What that means here is that I treat the vertices V1, V2, V3, 0, 1, 1 and V1 prime, V2, V3, 0, 1, 1. I think of them as the same vertices because I just give the provers instead of this tuple and bit strings, I just give this vertices which are labeled 1.
For the completeness, you don't need this information.
For the completeness, I will not need this information, which I will show. But what this means in terms of this graph is that I look at two vertices which correspond to different tuples, and I merge some vertices in these two hypercubes, which are these two vertices. This was one vertex of the unique game, this is another vertex of the unique game. This is the bit string there, this is the same bit string in another place, and I merge these two vertices. So the reduction no longer has gadgets, it's slightly different. What I'll show is that if we play the game like this, if we think of vertices corresponding to these deleted tuples in which we only give subsets, then I can get around this problem that the cuts in the original graph can destroy your soundness. Okay, is it roughly?
I mean, in the sense that you started from the original graph in the no case was an expander. So maybe already you can show that the constraint graph of the unique game is an expander.
Right. So we would like to show that. So we would like to show that if G has small set expansion, then G to the R has small set expansion. We don't know how to show it. What we can show is that I'll formally write the.
Like, is it just false or?
No, I don't think it's false, right? We don't know if it's true. I see. Oh, but then you have to think of how you allow the size of the set versus R. So if you allow the size of the set to be 1 over 2 to the R, then it's not a small set expander. But if you only require for slightly larger ones, then.
And this folding will fix that problem, like the cliques. So.
Yeah. So the graph actually about will be okay. Right. I'll write down the graph for which we are talking of the expansion here, and more generally in the reduction. So formally, given a graph, we'll be creating a sparsest cut problem. So I think of the vertex of the sparsest cut problem as something from V to the R and a binary string maybe. Then wherever there were ones, I retain the vertex. Wherever there was a 0, I replace the vertex by a bottom. So then my vertex set becomes this new thing, V union bottom to the R, right? And I sort of, this is the vertex set of my instance that I output, and all edges are between vertices of this type, which are just wherever there was a bottom, replace it by an arbitrary vertex and place the corresponding edges. So what I'll say is that suppose I am given a cut for this graph or a cut across this vertex set, then I can say that from this I can decode a cut from the graph obtained by the unique games reduction, where I replace everything by a hypercube, such that this decoded cut does not look like a cut in the original graph, but it actually passes through the hypercubes. So if you give me a sparse cut here, then that will give me an equally sparse cut here with the additional guarantee that it's not a cut in the graph, it passes through the hypercubes, at which point I can apply an analysis of like majority stable list or something. Okay, so what is the decoding? It's very simple. You have so given a function f from V union bottom to the R, which is a cut in this graph. I want to decode a cut. So for every R tuple A, I want to, and every binary string x, I want to be able to find 0 1 value, and I say G A of x is equal to f of w, where wi is equal to ai if xi is equal to 1 and bottom if xi is equal to 0. So
So first of all, what is A? But even before that, you didn't tell us what the.
okay.
Okay, so we have you didn't tell us what the edges are in this graph?
Right. So the edges are
The same graph as before. You
Well,
just
but you
identify
meant
vertices.
and you collapse the corresponding edges.
collapse corresponding edges.
And this decoding is nothing fancy. You just I mean.
Yeah, you unfold it.
So right. So I mean, you just look at the cut. It's basically.
So
I mean, just look at the. You just now force the cut. It's the same graph as before. You just force the cut to have the same value if two vertices agree in the same ones.
so the problem was that
All these vertices will go to one side, to the same side.
and so the problem was somehow the prover earlier could give you a cut without looking at this binary string at all, just looking at this. Now what we do is we give him a question which depends on the binary string. We delete parts of this question where the x is 0, and the prover gives us a cut, and we say, okay, now the cut depends on the binary string. And the prover says, well, I mean, I didn't have a choice because the question you gave me was masked by the binary string, or parts of it was deleted. But that's just it. We just modify the question so that the cut depends on the binary string. So is the graph okay now? Or?
So x is a binary string. Okay. So that's the value of the cut in the original graph.
Yes. So this GA of x is a cut in this graph. F is a cut in this instance which we actually output, and what I want to say is that GA of x is balanced. The way I want to say it is expectation over A variance of GA is say larger than 1/10. If given that expectation of FA is between say 1/3, F is between 1/3 and 2/3. So F is a balanced cut. If that is true, then GA has a reasonable variance over A's, which means that at least in 1/20th it has variance 1/20th, which is good. First, it's a quick thing to check. Expectation over A, expectation of GA is equal to expectation of F. Because each vertex of F, each input of F is just sort of some input of, like each input of G appears as an input of F many times. And so if I look at the distribution of the inputs of F, which is given by the by adding the corresponding weights here, then these two quantities are just equal by definition.
They're really just the same function.
They're pretty much the same function. Yeah. Yeah, I mean, except I want to think of this quantity. That's all. That's why I write GA. Okay, so let's just calculate expectation over A. Which is the thing we'll be interested in to calculate variance. And let's see what this is. So if I unfold, and this part is okay. Where W1 and W2 are two tuples which are obtained from A just by keeping the bits where xi is 1 and replacing the others by 1. So, as A varies over all R tuples, W1 and W2 also vary over all tuples which have size roughly R over 2, because half the bits are masked by zeros. And in fact, W1 and W2 are related as follows. For every coordinate, so if I look at a coordinate of W1, the corresponding coordinate of W2 can be obtained by applying a Markov operator, which is the following. If the coordinate in W1 is some vertex, the corresponding coordinate in W2 is the same vertex with probability half, because with probability half, x1 and x2, given that x1 is 1, the probability that x2 is 1 is half, and so you get the same vertex. With probability half, x2 is equal to 0, so you get bottom. If x1 is 0, given that x1 is 0, x2 is 0 with probability half, and x2 is equal to 1, and it is a random vertex with probability 1 over 2n, because this being bottom did not tell you which vertex I was talking about. So, W1 and W2 are two random elements of V union bottom to the R, which are related like this, and this is some operator M which acts coordinate wise on the inputs of F. Right. So, this is a tensor operator, and all I am asking is the second eigenvalue of this, or I mean right now I am just looking at this. I will be interested in the variance which will come from the second eigenvalue. And I know that the second eigenvalue of such an operator is the second eigenvalue of the one coordinate copy. Right. So, I can just look at one coordinate. So, I am only interested in calculating the second eigenvalue of this single Markov operator. Let us call it lambda. I will calculate it in a minute, it is probably easy, but let us just say it is lambda. Then this is less than equal to lambda times expectation of f square plus 1 minus lambda times expectation of f whole square, or I want to upper bound this. No, so if sorry, I want to show that there is some variance in each coordinate, but if it was constant, if GA was constant in every A, then this would be equal to expectation of F. I want to say that this is significantly lower than the expectation of F, it is more like the expectation of F square. I mean, okay, let me just say why this is equal to, why this gives you something about the variance. This is the variance, right? What I am upper bounding is the negative term in this expression, so it should be upper bounded. And GA square is again binary, so GA square is GA and this is just expectation of F. So, this is equal to expectation of F minus that quantity which I just upper bounded. So, this is greater than equal to minus lambda times expectation of F square is just expectation of F, because F is Boolean, and so that's just 1 minus lambda times variance of f. You get expectation of f times 1 minus lambda minus expectation of f's square. So that gives you a lower bound on the variance, and this quantity is just a fancy way of writing I guess expectation of f whole square, which is what you would get for the constant function minus lambda times expectation of f minus expectation of f square, which is what you would get for the part orthogonal to the constant function, or maybe 1 minus lambda plus. So this is what you get for the part in direction of the constant function. This is the orthogonal one. Okay, so basically just comes down to calculating the eigenvalue of this, and slightly easier to think of this operator if we say that instead of replacing it by bottom, we replace it by another random vertex, but attach an extra symbol bottom so that we know it's here. Yeah, so it's kind of nicer to think of an operator which goes from top comma 1 top comma n to bottom comma 1 bottom comma n, and so if I put it like that, I can put it the complete bipartite graph here with probabilities 1 over 2n directed. So with probability 1 over 2n, I replace it by a random vertex, and with probability half, I keep it a self loop for each of these. When there is a bottom, it just means that I have replaced the original vertex, which was probably coming from some unique games construction, by a completely random vertex which has no information. And now this is kind of nice because the matrix of this is something like half times the identity plus 1 over 2 n times 0 j 0, for which you can calculate the eigenvalues. The second eigenvalue is half, and so you get this bound with half times the variance, which means that if the variance, if f has expectation at least 1/3, the variance in some constant, and so you get that the variance of this function on the graph is some constant, which means that at least say in 1/10 of the fraction of the hypercubes the cuts are balanced, and so either in all those 1/10 fraction you cut square root epsilon fraction because of the cuts, or you have some influential variables, and if you have influential variables then you can get a good assignment for the unique game, which cannot happen because the original graph had non-expanding sets, because the reduction of Prasad and David will say that if you get a good assignment for the unique game even satisfying 1%, then you can find a small set in the graph which does not expand, and that would be a contradiction. So the rest of the part is you just fit in what is known. This is sort of the new trick that is happening, that is all. Is it okay so far? Yes, that is because those weights on these edges, it replaced by a random vertex, the n vertices.
So the sum of edges going like from one vertex is half staying inside and half going to a random place.
Yeah, so the n random places to go, each with probability 1 over 2n.
So this lambda, this was lambda to the r?
No, the second eigenvalue of this rth power of the operator is just 1 lambda. There is no power of r here. Okay.
It doesn't rely at all on the structure of the original graph.
No, so that's the
Make sure that these things are balanced no matter.
Right. So this part is not really using the fact that the original graph had no small non-expanding sets. It's just using the fact that the strategy in the completeness case, which I'll just show in a minute, depends on a set of variables. If you are given a set of variables, if I removed half of them, for the remaining half you still have that strategy. If there was a reduction from unique games to say triangle free sets, or like from triangle free sets to unique games, this part would still make sense, except the reduction would probably have problems. But
So that's very nice, because basically you're saying something like the cuts that kind of respect the hypercubes are kind of special, so you somehow ruin all of them and without really looking at whatever graph you start.
yes. Okay, so the completeness strategy is easy. Originally we were given r vertices. Now what happens is only r over 2 of them have something other than a bottom written in them, and the rest are just junk. So the provers ignore those vertices, just look at some part where there is non-bottom, and think of look at if there is a vertex from the non-expanding set in this part, non-expanding set in this original graph. If there is, they answer this index, and if not, they don't answer it, and they just ignore this. So it just changes. Maybe you can say that you increase r by a factor of 2 because you can choose r given the size of the non-expanding set. So you just play around with that. What it really changes is in that non-expanding set, how the m, which is how much around delta are you allowed to assume non-expansion, how that fluctuates. So that maybe grows a little by a factor of 2 or something. So that's the reduction basically. This doesn't give you the optimal version, sort of the version I claimed, the partition version. This just says that you can find a sparsest cut. In the completeness case, in the yes case, when there is a non-expanding set, there will be a sparse cut of size 1 over e, which is the probability that they will find one unique vertex, and will have epsilon fraction of edges crossing it, where epsilon was how the binary strings were perturbed, or whether there is a bottom here or not. Maybe there is a bottom here and there is not a bottom here, because the binary string 0 1 was perturbed by epsilon, what was sent to the provers. So they are looking at slightly different copies of the sets. And in the no case, what you will get is that 1/10th fraction of the hypercubes, or some constant fraction of the hypercubes, have no influential variables, and so there the cut is essentially what it will be in a Gaussian graph, or in a perturbed hypercube with no dictator cuts. And so you will get that Gaussian kind of expansion profile that I wrote, which is just it will be divided by some large constant here, because I haven't optimized the parameters, but it will be something like square root epsilon in the end. This will be the measure, but okay. Let me just say what's the optimal way to do the reduction, and not necessarily need to do the analysis, it's just the same. So what we were doing here is we had
When you don't want to lose, what are you trying to not lose now? This factor.
so first of all, this is the problem, that we only get a cut of size 1 over epsilon. We are not allowed to choose the size of the set. In the original way, somehow had a control over q. That's the main thing. Other than that, there is some optimization here, but that's not so important. In the final reduction, we can get a much better concentration on the variance of g. In fact, we can get that the expectation of ga whole square is very close to the expectation of f square, this lambda can be made arbitrarily small, and that is the other optimization. Okay. Where is this coming from? So, here what we were saying is that you have an alphabet of size 2, you use the zeros to identify vertices in the unique game graph and the ones to ask a question, which is this is the set of vertices where there is a 1 and answer me there. So, now what you can do is you can look at an alphabet of size, deliberately write it as q over beta. You use the symbols 1 to q to ask a question, and q plus 1 to q over beta to identify vertices, which means that if you get something in this range, you put a bottom there, and if you get something in this range, you leave it as such.
So that will reduce lambda to beta.
That will reduce lambda to beta, because it just changes the weight in the bipartite graph. Okay. So, what we now do is look at an R tuple of edges, which comes from the reduction from small set expansion. Then we pick two strings, one which has elements between 1 and q, which is the, and another which has, so we pick the string from so we write down symbols between 1 and q, and we also write down top and bottom. Wherever there is a bottom, we will just replace the vertex by a random vertex later, but and we choose bottom with probability 1 minus beta and top with probability beta. So, this is what we look at, and then the provers basically look at the beta fraction of vertices where there is not a bottom, that is the relevant part, and work with it. The eigenvalue, as I pointed out, can be made as small as lambda, which says that the expectation square is very close to expectation of f square. So, all the errors become very, very small. You get a promise on in the no case when the measure of the set is bigger than beta at least. So, when it is less than beta, when expectation of f becomes much smaller than beta, then this kind of bound does not mean anything, then it is very weak. So, to make any useful conclusion, the measure of your set in the no case has to be larger than beta, which is where the delta parameter in the result, that the set has to be sufficiently large for any conclusion to hold, but that is something else you can choose. That is okay. Why do not we get this? Now we think of this as divided into k parts, which is also k is another thing that we will choose. So, we divide it into pieces of size r over k and k pieces. Now, what, and we think of delta to be about, delta is the size of the non expanding set in the graph, to be about 1 over k over beta times r, which means that if in each of these pieces, which is about r over k, I only retain beta fraction of the vertices, then in expectation there is one vertex from the small non expanding set. So, there are k pieces, in each one of them there is one vertex from the non expanding set with probability 1 over e. Now, what the provers do is they choose the first, now the permutations that we do, so we permute this and we permute this, the permutations respect the pieces. So, the provers get the same piece structure, the k block structure, but within each block things are permuted, and they pick the first block where there is a unique vertex from the non expanding set in the graph. So, if there is a non-vertex, if there is a vertex here, the unique vertex, then the chance of having a unique vertex here is 1 minus epsilon, and so for each piece. So, with probability 1 minus 2 epsilon, they can pick a common block such that both copies of this block have a unique vertex from the non expanding set in the graph, and then they answer the index. So, the game is still the following, the same, they have to answer an index of a vertex, and so they answer the index of this vertex. If the noise parameter which changes tops to bottom, then this q is epsilon, then the loss we have in this correlated sampling is 2 epsilon. So, and up to that factor of 2, the result I mentioned actually matches an algorithm for finding small non-expanding sets in a graph, which was in the paper of Prasad David and Prasad Tetley. Okay, in that algorithm loses bigger constants, but so this result seems optimal up to the factor of 2. Okay, yeah, and this just becomes a little more detailed analysis, but the idea is still the same.